May we have your attention, please?
Welcome to the 6th episode in our series of podcasts on when software goes wrong. In the previous episode, we talked about an incident that happened on a city metro system while testing a new signalling system. After that incident, testing with the new system was suspended. In this episode, we'll refer to another real-life incident and use that to look at the lessons that can be learned from an operational system that's time and safety critical and carrying hundreds of thousands of passengers at any one time. And we could be talking about a train network, but today we're talking about air traffic control. We hope that this podcast will help you and support the rail industry to contribute to addressing the RAVE Cambrian recommendation, which included capture and dissemination of safety learning available from the reporting of complex software-based system failures. You can find out more about the Cambrian ERTMS incident that was investigated by RAVE in another of these podcasts. Today, I'm again talking with former rocket scientist and systems safety and risk engineer, Dr. Emma Taylor. We're going to look at this incident from the perspective of not only what happened and why, but how the way they developed and tested and operated their software contributed to the fact that they were able to return to normal operation in a matter of hours, despite failure of the primary air traffic control software system, and then almost simultaneous failure of the secondary backup system. There's always something to learn, even when things go right and safe operation isn't impacted. Software for aviation is developed over years, and its origin can be a decade or more ago. And so it is for rail. So we'll also cover recommendations that came out from that investigation because they're also potentially applicable to railway software projects. So Emma, welcome again to the RSSB podcast. Please set the scene for us and tell us why you picked this incident, if you will. What is it that the rail industry can learn from it?
Thank you, Ant. Some of you may remember back in 2014, the temporary shutdown of the airspace over England and Wales. Maybe you were flying over the UK or your takeoff or landing was delayed as a result. Now, this significant travel disruption was traced back to a single issue within 2 million lines of code, leading to the temporary failure of NATS, or the National Air Traffic System, at a control centre in Swanwick, Hampshire, which was responsible for managing all high-level flights over England and Wales, and of flights going into and out of all the London airports in southern England. Just to give you an idea of the scale of the event, more than 300 flights were delayed, and the number of passengers delayed by these initial delays, diversions and cancellations was around 65,000. This carried on into the evening and the next day, and was estimated to impact overall some 230,000 passengers. Clearly, by the end of this event, many aircraft and crews were in the wrong position. I read that actually for one operator, that was 50% of their aircraft and crews. And the air traffic control provider reported nearly 15,000 delay minutes. Now, it is important to note that this does not relate directly to the delay experienced by the passengers. But at the same time, the incident reports also notes that the total aggregate delay minutes attributed to this incident was broadly equivalent to a normal bad weather day event. Now, making the link between trains and planes, signalling is a control system in the same way as air traffic control, and there is always the need to consider performance levels while maintaining safety. When you have aviation, you need to control flights, takeoff and landing, and when you have trains, you also need to control their movement and timing to a schedule. Aircraft have virtual tracks in the sky, defined paths designed to keep them from colliding, in the same way that our signalling systems help keep trains apart as they run on the track. So how air traffic control addressed this issue might have some lessons learned that could be applied to rail.
Thank you, Emma, for setting the scene. We've talked quite a lot about the V model, which is integrated with the project lifecycle. In the previous episode, we talked about the city metro signalling incident. What are the significant differences between how it was used there and how it aligns with the NATS incident?
Let's set the scene. Let's look at the whole railway. So as more of the railway embeds digital systems in both infrastructure and rolling stock, and in the links also between infrastructure and rolling stock, such as in the signalling system, it becomes ever more important to consider the project life cycle and the steps that you need to execute in order to be able to ensure safe operation that allows you to also hit performance targets. Now, the project lifecycle should include a series of carefully structured steps. These include creating a concept and defining a system, setting the requirements and analyzing them for risk, thinking about the practicalities, design, development, manufacture, and installation, and then checking at each stage, are you building the right thing and are you building it right? Now, what we should be aiming for as each stage of this verification and validation process is that it is well completed and well documented. In this air traffic control incident, most of the earlier steps, as I read in the incident report, most of the earlier steps in the V model were done pretty much as well as they could be. But there was one latent error that had been dormant for a good number of years, and that was able to cause both the primary and secondary systems to shut down. As we step through that incident in this podcast, we can see how the fact that they approached their early stages in a certain way supported them in making a quick recovery. And so they were able to turn back time through those project stages to track down that small error in the 2 million lines of code that caused that shutdown of both the primary and the secondary systems. In parallel, they were also continuing operations because the planes were in the air, and we could cover a whole podcast with how they did that safely, but that's not the subject of this episode. We're looking at complex software-based systems, how to develop, test, operate, and maintain them, rather than emergency recovery. Of course, every situation is different. In our previous podcast, we explored an incident on a city metro system. In that case, the testing of the city metro signaling system, which, because of a number of factors outlined in the incident report, didn't work as intended. And in fact, the incident investigation might, in my reading, suggest that some of those earlier stages of the project lifecycle weren't completed as well as they could be.
Okay, thank you, Emma. The incident we're talking about here happened in slow time because the software was developed in the 1990s, and in fast time too, because from the moment the fault was discovered, when both primary and secondary systems shut down almost simultaneously, back to the resolution of full operation was just a matter of hours. What I find most amazing is that they were able to go through 2 million lines of code in such a short time. I'm also curious as to why that wasn't discovered during testing. In fact, it's an essential step in the V model, so did they jump over it?
Actually, no. And how it came about that that error in the code wasn't identified is definitely a question that they explored in the independent inquiry. And one line of exploration that they looked at was the categorization of software criticality, because that determines how rigorous the software validation and verification process will be for that module. Different levels of scrutiny apply to the different software categories. The immediate cause of the incident was identified to be a discrepancy between one number, which described the total number of controllers, the people that were controlling the air traffic control space, and the check on that number. The two weren't equal, and because the safety critical nature of this number, the number of controllers, if it wasn't right, the controllers weren't going to get the right data to control the aircraft. That safety critical nature meant that if this a checksum failure happened, it meant that both the primary and secondary software systems immediately stopped operating. Now, there's a lot more detail to it than that, and if you're interested, you can read it in the incident report, which is publicly available. In a nutshell, as I sat there and read the inquiry report, for me, it seemed that they had got the principles and implementation of categorization right, along with a hazard identification. There is a subtle point that if the code had flagged up this error, it would have likely been brought to the attention of the engineers for exploration. But this check was mainly designed to deal with hardware-related problems, and so it was unlikely the software designers would have thought about this during the development.
So it seems they had implemented the main stages of the V model consistently. To my understanding, they hadn't perhaps considered software-driven failure in the same way as a hardware-driven failure, which of course would include the consequences of increasing the number of air traffic controller workstations. But they had validated their system, including safety acceptance and commissioning through to system acceptance, operations, and maintenance. The V model stages had been stepped through. So how did we end up in this situation?
To answer your question, I just want to read extracts from the inquiry report. It is worthwhile highlighting the difference between fault finding in development and in operation. The fault was found quickly after the events of 12th December, which perhaps suggests it should have been found in initial review or testing. However, the situation is quite different, and it is perhaps helpful to use a needle in a haystack analogy. In initial testing, the staff did not know that this particular fault or needle existed, nor where to look for faults, needles of any type in hundreds of modules in over 2 million source lines of code. In contrast, on the 12th of December 2014, the staff knew there was a needle and the sort of needle to look for. The logs said that there was one and identified the type of exception. The logs also narrowed down the search to a few straws, counting the modulus as straws, or a few hundred straws if you consider each single line of code as a straw. Thus, the speed in finding the fault in operation does not mean that it was an obvious fault, rather than the failure and logging gave staff some good clues. We're down to detective work here. The inquiry summarised that there was not a shortcoming in the conduct of this aspect of the development process. There was a record of the history of the system's development and the changes that had been made to it over time.
So, Emma, if I'm involved in software development for rail, what is the thing I really need to take away from this? What I'm hearing is the need to have the documentation or systems in place to tell you what's gone wrong and where to look to fix it.
Yes, absolutely. You've heard correctly. And this issue of logging and recording as part of the recovery is a lot more substantial than people might think is initially needed or perhaps look to specify. In this case, that day's logs told them what had happened that day. But imagine if you had to go back a week or a month. All of that information would be needed to be recorded and retained. Specifying this to the level that's needed, so is in my mind just as important as specifying what the system needs to do when you're thinking of the system at the concept stages. I think it's perhaps even more important for software than hardware because of the sheer complexity and interconnectedness. Finding an error afterwards, it truly can be a needle in a haystack.
So, Emma, what can we do to help us find that needle?
So to help guide people in how to be able to find that software needle in a haystack when you need to, what I'd like to do is close out with some of the recommendations from the NATS report. Because with systems of this size, system testing of every combination of parameters is just not practical. There are many influences on the system, and it's simply not possible to test all the feasible configurations. We have to remember that no one can get it 100% right because of software latent errors, if nothing else, and because we're all human. But what I will do is highlight what I think from those recommendations it will be useful, good practice for the rail industry to have a recap on. First, what I call basic housework, basic technological housekeeping, keeping things nice and tidy and explaining what's what. One example is to improve naming conventions for data types and functions to make their intended use more obvious. 2, you should always work to ensure the effectiveness of the software development process, including integrating and testing software that is likely to be developed in a range of different software programming languages in different companies and in different countries. And to help with that, I should point out that software testing is now in itself a highly advanced discipline. There are all sorts of tools and processes that you can use. It's not just a question of running the code to see if it compiles. And the inquiry notes that there may be cost-effective approaches that automate some of the tasks that are particularly effort-intensive. One of the recommendations focuses on the need for a complete continuing evidence base, or CCEB, and the recommendations covers audits of this evidence base as well. The complete and continuing evidence base, this CCEB, is all the information that's necessary to evolve the software in the light of change requests and to carry out forensic analysis in the event of problems. Thus, it includes things such as specifications, architectural description, and verification results. That is evidently useful for aviation and so likely to for rail. In the Cambrian investigation of the signalling incident on ERTMS, there were some initial challenges found by RAVE in reconstructing the versions of the software developed and deployed, as well as accessing error logs after the event.
So, Emma, thank you. That covers the help that we can get and the automation to do testing once the software process is underway. But what can we do to ensure we get the right people to build the right stuff in the right way?
Of course, processes are key. When you look back at the V model, the project lifecycle, this provides a strong, rigorous framework for development and implementation of complex software-based systems. And in this series of podcasts, we've explored and analyzed where the causal factors, the underlying causes, have occurred at each stage of the lifecycle for the incidents that we've been discussing. But one thing we haven't addressed explicitly so far is the supply chain and the role of requirements, processes, and contractual arrangements. I think it's worthwhile relaying what the inquiry report says about this and the next generation of air traffic control systems. The inquiry pointed out that the industry is largely dependent on suppliers for their software, and that is the need to manage software quality in the supply chain. They do also note there is little point in defining processes that the suppliers do not or cannot use.
So that's the future, but what does that mean for people working with software today? Surely the solution is to have strict and detailed procurement processes for the supply chain with in-depth scrutiny and lots of standards being referenced. A really tough approach is good, right?
Well, I'm just going to take you back to the previous sentence where the inquiry report said there is little point in defining processes that suppliers do not or cannot use. A pragmatic approach is needed. The client needs to consider what it considers and believes are good processes and how it can mandate them on the supply chain. There is an interesting point in the inquiry about what it can assess retrospectively on existing software code and what it can encourage suppliers to adopt and how it ensures in both quality and execution and in contractual terms too that the process is implemented correctly. There is a particular focus on implementing newer testing technologies, and they point out in the report that the strongest argument is likely to be economic. If it can be shown that faults are detected and removed more cost effectively with new methods and tools, then it is perhaps more likely that companies will accept this technology. And we're getting to one of the thorny topics associated with software, because development happens over years, if not decades. And so we come back to this challenge of turning back time, which is why the V model structure is so important.
Thank you, Emma. In previous podcasts and blogs, we've stressed the importance of reporting digital system-related errors, even if the fault isn't completely apparent or clear at the time. Underlying anomalies can be the start of a thread that you can pull to help you find the hidden needle in the haystack before it causes a software operational problem. How does that link with the inquiry recommendations?
So as I read the inquiry report, I saw words that recognised the practicalities of maintaining this evidence base. And although that you can place configuration control rules which say that the evidence must be there, in practice, things such as test results, retaining the information, it is of course possible in long-lived, geographically distributed developments for material to be mislaid. So you can't achieve this complete continuing evidence base or CCEB. So they propose a solution, an increased audit of the available evidence base, and for that audit to be of the evidence base itself and not just the verification evidence. This concept of evidence and audit of the evidence and audit of the verification is perhaps something worth thinking about, because the code in question in this particular incident has been the responsibility of 3 different companies in its life. And perhaps when you look at the long development cycle for the rail industry, you could find a similar situation. But you do need to trade off. More frequent audits increase cost, but also mean problems might be found sooner. And to pick up your point about errors, this inquiry's recommendation ties in well with Rail's collaborative approach to reporting of incidents and topics of concerns. And I'll quote directly from the report. NATS should consider introducing a formal error management system to capture anomalous occurrences that fall below the safety event threshold, but which may indicate where changes in systems procedures or training would benefit the management of risk.
Thank you very much, Emma. I think what we've covered in this and the previous episode have taken us nicely through a series of examples of how and how not to use the V model to step carefully through each stage of the development lifecycle for complex software-based systems. And of course, we can't stress this enough, the importance of recording, documenting, and retaining the whole lifecycle history, so that if you need to turn back time when something does go wrong, you can more easily determine what you're looking for, where to find it, and then determine how to fix it. I hope this has proved both useful and given our listeners something to take away and act on. Don't forget, if you want to refresh your memory on the Cambrian incident or the incident on the City Metro system, you can listen to the 2 previous podcast episodes. If you have any questions or comments about this or any other podcasts, please contact us by emailing podcasts@rssb.co.uk. But for now, thank you for listening and goodbye.